Hello and welcome to Causal Python. I'll be your host. My name is Hanan Shteingart and I work for Vinai, where causal inference is essential to what we do, which is making better decisions using data. A short summary of this deck would be as follows. If you take data and you add assumption on it, causal assumptions, you can use this data and a method called causal inference in order to make a better decision. And this is I think the very high pillar or the holy grail of data science essentially is to help decision maker to make better decisions. Now a real workshop on causal inference could be very long. For example, on the lab in Microsoft, and it was a whole day. I will try to squeeze the very essence of it into 45 minutes, so good luck for me. The agenda for today will contain 3 parts. Part number 1 would be the motivation. Why should you care and why you should listen instead of doing another coffee? So the second part will be the theory. This will be the main part of the talk. We'll explain what is causal inference, how is it been done, what assumption do we need in order to do it. And the last part will be a coding session where I'll show you actually code of how can you do causal inference. So point number 1, let's start with why you should listen to me and why causal inference is important. When you think about it, every manager on earth has some KPI that he is measured by, and he is not a passive observer like in supervised learning. The manager can actually take actions in order to prove the KPI so he can get better or she can get better bonuses. So this problem is also called the problem of policy optimization. A policy, how you make actions, and you want to improve how you make actions to get better KPIs. Okay, now let's prove this point with data. I claim that we have KPIs and action, and what we really care about is how to improve those KPIs using action. Now, McKinsey Company published a paper which value in dollars unlocked per vertical in the upcoming years is mainly in 2 verticals. One is called marketing and sales, and the other one's called supply chain management and manufacturing. Now, even without being an expert in those fields, you know that in both of them you have some KPI, like it could be conversion rate or lifetime value, it could be the throughput of your supply chain and the throughput of your manufacturing. And these KPIs are a function of the action that you take, the campaign that you run, the salespeople you hire, or the machine that you use in your supply chain. So again, it seems like the 2 most valuable verticals for AI includes actions and outcomes and nothing about predictions. And this is where causal inference and reinforcement learning shine. Now let's make it more concrete. There are actually 3 types of analytics flavors. For x-axis you can see the difficulty, on the y-axis you can see the value. And let's list those. The first analytics type is descriptive analytics, where you can take data which was recorded and just see what's going on there. The second one, this is like tools like Tableau and others. A predictive analytics, on the other hand, will tell you what will happen, like predicting the weather, what weather will be tomorrow. But it's a passive view on the data. You cannot control the weather, you just predict it. The prescriptive approach will tell you where should you seed clouds in order to maximize the amount of waterfall. So I claim that this is the most important question, where you actually learn what you should do in order to get the best result. However, although prescriptive analytics seems to be the most valuable approach in analytics, a survey by Causal shows that actually most data scientists use different supervised methods, but very scarcely they use other methods which could be included. So there is some gap between how useful and what is the potential value out of these methods versus how often is it used or known by a common or citizen data scientist. Now you don't have to believe me, you can believe others who are more experienced and more well known. Susan Ethay is an economist professor in Stanford, and she claims that there is, in a science paper, she claims that there is something beyond prediction, and this something is to use big data in order to learn better policy. Policy meaning making better action in a certain situation. And on the other hand, most of you already know Joshua Bengio, who is like got the Turing Award for deep learning, and he also is focused recently in his research about the question of why, or the question of causality. Of course, I didn't mention Judah Pearl, who also a Turing Award winner, and he invented causality. Now, don't believe me too. It's not only that academia talks about it, also companies, large digital native companies talk about using causality in order to do things that they cannot do in other ways. Here you can find quotes from Uber, Netflix, LinkedIn, Booking, and Airbnb, but there are many others. Now let's think about what resource can we use to make better decisions. So the gold standard in science and in general, in data science in particular, is to use experiment. If you can just toss a coin and see whether to treat or not to treat, to send an email or not to send an email, and so on and so forth, then you have the gold standard in causality. You can just measure the effect very easily, see the outcome when you treat, see the outcome when you don't treat, compute the difference, and that's it. Of course, it's a bit more complicated than that. Ronen Kohavi is like the superstar in experiment about how to do experimentally correctly. But assume that you cannot do experiment. What else can you use in order to make better decision? Well, if you really know the physics of the world, and you can build a simulator, like a plane simulator or a mechanical simulator or so on and so forth, a chemical simulator, a protein folding simulator, then you can come up with a policy to improve your KPI by playing with this simulation. This is what DeepMind did with Atari games. But if you can't experiment because maybe it's not moral, or you cannot simulate because the system is too complex or unknown, then all you have left is data, which usually you have in abundance. How can we use observational data in order to make better decisions? This is where offline reinforcement learning and causal inference shine. So now for theory. As I mentioned before, there are these three types of analytics. Let's see how do they translate into equations. So in descriptive analytics, we care about the distribution of a variable. In predictive analytics, we care about the conditional distribution of variables, how y is conditioned on x. So x could be the image that we see, and y could be the animal type. So we predict what animal it is given the image. In prescriptive analytics, we care about what is the outcome of an action. So what is the lifetime span of a human being with this blood test, whether I give this user, a human or patient, a medicine or not. Another way to look at it, it's that supervised learning is more focused about the prediction itself, but causal inference is more focused on defining the underlying generative model, meaning finding out how reality works, and so we can not only predict y given x, but we can predict y given x when we do something. So in this equation, just to confuse you, x here is the action, and in this equation, beta, which is the coefficient of the action, is actually what we care about. We care about how does making an action x equal 1 or 0 affects the outcome, rather than focused on something like minimization of a mean square error or whatever. Let's watch a short clip from the movie Sliding Doors. Until the movie starts, I will talk about the fundamental problem of causal inference. Well, the fundamental problem is that we can see what actually happened when we did something, but we don't know what would have happened if we did something else. You can treat this as a missing data problem. For each individual, treat or not treat, and we see only the outcome of what happened accordingly. So in some sense, we don't know what would have happened if we did something else. In this movie, you can see the father and daughter going up the stairs, and the daughter disturb the actress getting into the train, so she misses it. In another identical world, the father actually noticed that the daughter disturbed this woman going down the stairs and move her aside. You will see it now. So the woman goes down the stairs, the father and daughter gets out of the train. The father, noticing the daughter is disturbing, he moves her aside, and now the woman makes to the train at time. In this movie, you will see that the effect of this action, the difference in potential outcomes is huge and enormous and affects this woman's life. Now, in an experiment or in a data set, we will have the outcome, the treatment, but we will only have the potential outcome of what we actually did. So if there was no treatment, we know the potential outcome of no treatment, but we will never know what is the potential outcome of treating. And vice versa, if we treated, we know the potential outcome or the factual of treating, but we don't know the counterfactual of what would have happened if we had not treated. And thus, computing the difference between the two, between the potential outcome of doing an action minus the potential outcome of not doing an action, is unknown. This is the fundamental problem of causal inference. Let's have a short crash course on causality main concept. Again, this would take a whole semester if we will do it in depth, but I just want you to have the gist of it. The first concept is called directed acyclic causal, where every node is a variable and the edge between the node or the arrow represent the causal relationship. If A is controlling B or affecting B, there will be an arc starting from A ending with B, an arrow. If B is not affecting A, there will be no arc. For example, we know that if we go up a hill, the temperature will go down. So the altitude actually affects the temperature, but we know that the other way around is not true. If we change temperature by an air conditioner, it's not like the altitude will change. The second concept is called causal discovery. When we don't know the causal structure of the world, we can actually use algorithm in order to learn this causal structure from data. Now, it was proved that this is in fact impossible theoretically, but practically if you introduce some relaxing assumption, it can be done, and people have been using causal discovery both in manufacturing and in biology and system biology and in other fields. Potential outcomes are, as I mentioned, the outcome of what would happen if I do an action or if I don't do an action. These are imagination of the different outcomes that could have happened, but we only seen one of them. The one that we see is the factual outcome, and the one that we don't see are the counterfactuals. The effect estimation, or the average treatment effect, is the difference in the expectation of the outcome, whether we treat or not treat, or whether we treat with treatment A versus whether we treat with treatment B. Now, this effect could be also depends on the characteristics of the patients. Medicine could be very effective for male, but ineffective for females, or very effective for young people, but not effective for older people. When the effect depends on something, we call it CATE, conditional treatment effect, or the individual treatment effect, or the heterogeneous treatment effect. These are all names to represent that the effect could be also a function of something. Policy evaluation is the process where we take a policy, which is the transformation between what we observe, the X, and the treatment, T, and we measure how valuable or what would be the outcome if we follow this policy. Now, of course, if we can do that, we would like to, if we can evaluate policy, the next logical step would be to find the policy which maximizes the outcome. So let's assume outcome is the revenue or engagement or anything else we care about, lifespan. We would like to maximize the lifespan of the patients by selecting a policy, for example, a medical treatment, given what we observe about the patient. Now, why causal inference is hard? Well, it's hard because there could be many pitfalls. And one of the major, most famous pitfalls in causal inference is that causal inference could be very biased if you take some variables into account or don't take other variables into account. So there are specific variables that you have to enter into your model, otherwise your estimation will be very biased. And the other variables that if you do take them into account, your estimation will be biased. For example, on the top left, you can see a most famous example for a bias called the confounding bias. If we have some variables that controls both the treatment and the outcome, we have some backdoor issue where the effect of exercise on lung cancer could be biased if we measure it naively by this third variable, which actually influence both. If we take some very complicated DAG, very complicated causal relationship between variables, it's very hard to know what to control for. And for this, Joshua Pearl invented something called the do calculus, which will help you to understand what variables you should control for when estimating the effect between some action and some outcome. This process is called also identification, which is like a recipe of how to estimate the effect. If we will not follow this recipe, totally wrong result of the effect of this variable on the outcome. Consider this compared to supervised learning, where you just care about the accuracy of your prediction. Here we care about the accuracy of the effect estimation. And some variables could be very misleading, and we should either take them into account or don't take them into account. And if we do not follow that, we will get a very biased result. So now a quiz. Let's assume that we know that exercising more increase cholesterol, and we shows in a scatter plot that actually when the exercise is higher, cholesterol level is higher. What could explain this? What could explain what's wrong in this DAG where the treatment exercise influenced the outcome cholesterol? So you already know the truth that there is some kind of a confounder variable. There is some variable, for example age, which affects both the treatment probability and the outcome probability. In this example, the older you are, the more probable are you to exercise and the more level cholesterol level you have. So per strata, per age, the effect is negative. The more the exercise, the less the cholesterol level is. But again, you can see here this confounding bias, which in this case is called Simpson paradox, where the effect seems positive when you just take into account the treatment and the outcome. But when you control for a confounder, the effect is actually negative. As mentioned before, identifiability is the process of taking data that you collect, your observed data, and turn it into estimation of effect. In order for this to be possible, we need to have some assumption on our data. The first one is called the Sutva assumption, which is very basic. It just says that if you act on one individual, it does not other individual. So the actions are independent, and also the outcome. Treating on individual J does not have an effect on individual I. Consistency means that it's also very makes sense that if we make an action A, the outcome that we will see is actually the potential outcome. So making an action actually reveals the true potential value. So it's your turn now. Let's have a small quiz. Which assumption is depicted in this picture? If we always treat pregnant, it's not good. If we never treat if allergic, it's not good. But if we sometimes treat if there is pain, it's a good data set in order to estimate effect. So, of course, the true answer is positivity. Positivity assumption talks about that every action has a probability larger than 0 to happen to every patient. Now let's talk about how do we estimate effects. So it can be shown that there is a relationship, if our assumption holds, there is a relationship between the data which we observe, like expectation on the sample, and the potential outcome. How? If we use both consistency and ignorability, it can be shown that this expectation over the data is identical to the potential outcome given some x. So if we condition on a strata, if we condition on a subpopulation we have the same x, and x is known to be the adjustable set, like if we control for it, there will be no biases, then we can just measure this conditional expectation, average them, weight them according to the probability to see those x's, and if we compute this expectation, we will end up with the expectation of the potential outcome. So we can do what's called identification, where we estimate something which is a potential outcome using a data set that we can see. A different way to do estimation of effect is to use what's called matching. And in matching, we take the high dimensional data that we have for each patient or user, And we, for each one that got treatment, we look for someone who is an identical twin but who didn't get treatment. And if we do this again and again, we will have a data set which looks as if it's RCT, as if it's a randomized controlled trial, because the probability to get a treatment and not get a treatment is equal. There could be some individual where we don't find a match to, and then our estimation is only applicable to a subpopulation out of the entire population. So this is again related to positivity. If for some individual we always treat, we don't know what would have happened if we didn't treat. So we put this subpopulation aside. This matching is hard in high dimension. If you took my supervised learning course in Yandex, you would know that in high dimension there is no notion of similarity or being close or far away. Sorry. So instead we can do a dimension reduction and use just one dimension to find matches instead of using the high dimensional data. This is done using something called propensity matching. Propensity matching is a fancy name for just a model that predicts the likelihood to get a treatment. So let's assume that A is the treatment, whether it's 0 or 1, and the propensity is just the probability to give a treatment given that we know all the covariates of the patients, like age and so on and so forth. It can be shown, I will not show it here, that if you condition on the propensity has the property which is called balancing score, meaning the distribution of X, if we control for propensity, is equal whether you treat or not treat. And again, this looks like RCT or randomized controlled trial, because if we condition on the propensity, it doesn't matter if you treat or not treat, the distribution of the patients or the units is the same. Last but not least, there is a method called IPTW, inverse propensity treatment weighting, where we weight different samples differently according to the inverse of the propensity. It can be shown that 1 and 4 are actually equivalent, and this is a technical point 2.3 in this book called What If. I also put it in the appendix of this deck. What is the inverse propensity weighting? Essentially, it says something as follows. Let's assume that we have red people and blue people, and we see that the probability to get treated for the red people is 75%, whereas the probability for getting a treatment if you are a blue person, it's 25%. So in order to estimate the effect, we cannot just average over treatment 1 minus average over treatment 0, because the average over treatment 1 will be governed by the red people, and average over treatment 0 will govern by the blue people, so we might have some confounding bias. So in order to fix that, we will clone the blue people. Instead of taking it just as a single data point, we'll treat it as 4 data points when the treatment is 1. And when the 3 red people, we will treat them also as 4 people by multiply it by 4 third. Again, for treatment 0, we will duplicate this individual as if he was observed for 4 times, and we'll take these three individual and weight them as if they were 4 individual. And this is what this equation says, is that to compute the expected treatment effect, average treatment effect, we'll just sum over the outcome, and we will multiply it by a weight. Which weight? If the action was 1, we will multiply it by 1 over pi. If the action was 0, we will multiply it by 1 over 1 minus pi. So there is a notion of better prediction does not necessarily mean better effect estimation. And here I show some example to make it more understandable. Let's assume that you are a data scientist working from some marketing department, and there are 3 types of campaigns: doing nothing, doing campaign 1, or doing campaign 2. And you have 2 models, and you measure the mean square error. Which model will have a better mean square error? Well, it seems like model A will have a better mean square error because it predicts the value of these campaigns better. But if you will need to decide which campaign is the best one in order to move budget towards this campaign, it seems like model A will be misleading because it will tell you campaign 1 is the best one and you should put more budget in that campaign, where in reality campaign 2 was the best one and you should move budget towards that. So model B, although it's less accurate in mean square error terms, it's more accurate in causal inference perspective, meaning the estimate of the effect over doing nothing is better for model B than model A. This is an example why causal evaluation is hard, but there are other things. First, there is the fundamental problem. We don't really know the effect because we don't really know what would have happened if we have done something else. So classical methods like cross validation is impossible. We need to find out other ideas how to measure how well are we doing in case we don't have experiment as a gold standard. This brings into attention a method called refutation, which is actually a family of methods in order to validate our model, the causal model, and to get more trust that what we are predicting as the effect is trustworthy. There are many methods to do that. Placebo treatment, where we just introduce some random treatment and we'll see that measurement of the effect is 0. So this is kind of a sanity check. We can also introduce some additional confounders, which are random, in order to see how sensitive is the estimation to confounders. We can look at subset of the data and see using bootstrap methods to measure how stable is the effect that we measure, and so on and so forth. And these methods do not actually evaluate how accurate our model is, but it allows us to gain trust on its applicability and to validate it. An application example. So uplift modeling is, I think, one of the best usage of causal inference, or one of the simplest one. And in uplift modeling, instead of predicting, for example, who will churn, we predict who is most likely to reduce its churn probability due to treatment. And the way this model works is that we estimate Kate, we build a model for the effect given that we treat or not treat, and then we sort or rank users according to the effect size. And if we will do that correctly, then once we treat subpopulation, we will treat only the people who are pursuables, people that we can actually reduce their churn behavior. Then we will start treating people that it doesn't really matter whether we treat them, because either they are lost cause, they will churn anyway, or they are sure thing, they will not churn anyway. And last but not least, if we increase our treatment population, we might even start to treat people who are called sleeping dogs, where if we treat them, the treatment effect will be negative, meaning they will be more likely to churn if we send them a message rather than not sending them anything at all. Causal ML is one of the Python package which is focused on this sub-problem of causality called uplift modeling. What are the typical stages in a causal project? First, we need to come up with some model or assumption or graph which represent our knowledge of what affects what. If we don't have that, we will need to use method of causal discovery. For example, there is a package called CausalNex, which is focused on that. Then we will need to do something called identification. We will need to turn those assumptions into a recipe of what should we control and what variables should we take into account for estimation. Then we need to do the estimation itself, estimating the effect. And last but not least, we need to refute and validate and check the robustness of our methodological way. Something that I have not mentioned is the positivity. Again, we need to take care and look for whether we can make our estimation on the entire population or only a subset of the population. Summary. Let's talk about supervised learning versus causal learning. So in supervised learning, we predict just the outcome given some covariant. And in the causal inference, we don't care about the outcome itself, but more about the effect of changing some action and what will be the change on the outcome. So we care more about the deltas and not the absolute value. The assumption in supervised learning that is we are a passive observer, and in causal inference we are a decision maker. And this creates a lot of difference and making causal inference much more difficult, because in supervised learning, we assume the train and the test data are equally distributed. This is one of the strongest assumptions in supervised learning. But in causal inference, this actually does not hold, because the data that you train on is not necessarily the same distribution as the data that you will actually have once you make different decisions, because the fact that you make a decision will change the distribution of your data. Validation in supervised learning is also very easy. You just do holdout sets and cross-validation. In causal inference, the validation is the fundamental challenge. We don't really know what is the real effect. So the only way to actually validate things is via experiment, but we can use refutation and other methods to validate the model and make sure it's not, we don't see some random or noise effect. The feature set in supervised learning has a quantitative effect. So if we take one feature off or on, the performance of the model could be better if we are underfitting, but if we are overfitting, then taking some features out could be help the performance. But in causal inference, the feature set is detrimental. If we take some variables out, we could have biases. If we put some variables we shouldn't put in the model, we could have a bias. So making sure that we use only the features that we are allowed to use in the estimation is very crucial in causal inference. Domain knowledge in supervised learning is nice to have. Sometimes we use features which were given by domain knowledge, but if we have a lot of data, you don't really need the domain expert. Like it was shown in ImageNet in other competition, where if you let the neural network decide the features for you, it's good enough. But in causal inference, you do need the domain knowledge, because otherwise you don't know which causal assumptions to take, and this could again affect which variables you will use and which not. And last but not least, as I see it, supervised learning is some kind of solved problem, and it's not what really the world needs. What the world really needs, and the world I mean businesses needs to be told what action to take and not what will happen tomorrow. And for this, we need causal inference. Now we will move to the practice part, the part that you will all been waiting for. So first, about the packages in causal inference. Let's compare here scikit-learn versus the 3 top most common infrastructures in causality. So first, you can see the scikit-learn is like about 11 years old, where the causal platform packages for Python are only 2 or 3 years old. You can see the popularity is much lower than scikit-learn, and you can see regarding the usability, I think that on the y-axis you have total number of stars. You can see scikit-learn is like 45,000, and all the other packages are much lower in their popularity. I guess my video here hides the information, but believe me that the number of stars is very low. So I will not go one by one on these packages. It will take me a lot of time to explain all the assumption and the syntax. So I just recommend you to read the fucking manual and learn these packages yourself. But I would like to show you some Python code which does the estimation with native Python, so you will understand the methods better. Let's have a look now on real data and real code. It's a famous data set called the Sex Bias in Graduate Admission from Berkeley. It was published in Science magazine in 1975, and it's a good example for the Simpson paradox that I've mentioned in my talk. So the first thing we do, as always, we load the data. Here the data is very small, so I just use the text format of the data, and I read it from the text directly to a data frame because the data is in CSV format. So the data is as follows. We have a different department in the university. We have the number of male that got accepted to the department, the number of men that were denied, rejected, number of female which were accepted, and number of female who were denied. The first step in the analysis would be as follows. We will convert the format into a tidy format. This is what this small snippet does. It converts the data so that each row is a unit. Each row is an individual, and for each individual we know the department, whether it's a male or a female, and whether it was admitted or not. So we have 4,500 rows. This will make the code of the analysis much simpler. And I encourage you in general to use tidy formats, as it will allow you to do analysis faster and in a more generalized way. Let's start with a naive approach. What will happen if we just compute the difference in expectation of admission or the admission rate per gender and just compute the difference between those? So this could be done in pandas just by grouping by the gender and then taking the mean over the admissions. And we can plot that very easily in pandas using the plot command and using the kind bar. And we can see that the admission rate is higher for male versus for females. And if we compute these expectations, we can see the difference is 12%, which is very large. So the conclusion, which I will show you is wrong, is that there is a bias in the admission to favor males over females. Let's now see what would be a causal estimation of the same effect, the effect of gender on admission. So one of the methods we learn about is called standardization or stratification. It's the same thing with different names. The recipe is as follows. We first need to estimate the probability of X, probability of each department. This is done again using the group by or the functional value counts. And we have the probability to be in each department. Then we will compute the probability to get admission per department and per action. So this is depicted in this head of this data frame where for each department and for each gender we know what is the admission rate. Now to estimate the effect, we will compute the multiplication of P of X, probability to be in each strata, times the conditional expectation in each strata, and compute the difference between the genders. And what we will see here is that now the effect is negative, meaning males are less probable to get admitted when we control for the department. And this makes sense because the department could both influence the probability for a gender to some gender to apply, and also the probability to get admitted, because some departments are easier and some departments are harder. A different method could be something that I didn't talk about in the lecture, but it's very common as well. It's called regression adjustment. This might look very familiar for you because it looks almost exactly as supervised learning. But again, as I mentioned in the talk, which features you get, you take into account when you do this regression, and which you don't, and which regularization method you use could have a determinantal effect on the biases that you will measure. So use this method very carefully, and only if you know what you're doing and which features you include and which you exclude. So here we just use logistic regression to model the admission as a function of whether a person is a male or female and which department. And this C denotes that this is a categorical variable. Now, the coefficient of being male is minus 0.2, but this is not the effect in difference, but the effect when we talk about the relative ratio effect, meaning the probability of being a male divided by the probability of being a female. But this is not how we measure stuff. So in order to measure it as an effect in difference, we need to convert this coefficient into a difference, and this is done using the sigmoid function, as I done here, and you can see the effect is minus 0.4, very similar to the approach that we did with the standardification. Again, this effect shows that the probability for a male to get admitted is smaller than the probability for a female. Last but not least, this is the IPTW approach, where we first model the probability for being a male given the confounder. So the action is being male or female, and we model this propensity model, and now we can have the prediction, meaning the probability for each individual to be a male or female given the department, and use this probability to find out the effect by multiplying the outcome with the equation I've shown in the theory part, which actually weights the different samples by the inverse of the propensity. And once we do that, we come up with an effect which is almost the same, about 0.4%. So to summarize, it seems like when we do the naive approach of the effect, it seems like females are more likely, male are more likely to get admitted. So if you can choose your gender or make the gender as an action, it's better to disguise as a male. But when you take into the account the confounder, the department, it seems like it's actually the effect of being a male reduces your probability to get admitted. So I hope you had fun. You learned about why causal inference is important, a bit about the theory behind it, and a little bit of practice with code. And I hope this will session convince you to get deeper insight about causality. Of course, if you are interested in this field, you can feel free to contact me and see whether you can also get a job in VNI, where causal inference and reinforcement learning are in the essence of what we do. Thank you very much, and have a nice conference. PyCon. Bye. Last but not least, this is the appendix I promised you, which proves that inverse propensity weighting and stratification are actually the same thing, and they are equivalent. This is taken from the book I've mentioned before, called What If?